Okay, so we're going to be continuing on with the 5.4 and 5.5 story problems that we started on yesterday. If you need to reference back to the material that we started going over, here is the same stuff. Here's the notes that we have written out. This does list Math 97. We are in Math 72, but there's a lot of really great crossover that goes in with a lot of these that is used in both 97 and 72. So that's where this is listed in here. But we are in the 72 stuff with this. So we went through our first example here was a mixture problem. So our process for that can be found in the video from yesterday. We are moving on into our second example. We're going to have three total that we're going to go through today. So our first one here, looking at number 2, Michael, Franklin, and Trevor are attempting to get away from a local motorcycle club. They decide to lose the motorcycle club members by taking 2 boats from the same dock and splitting up along a river. Michael and Franklin take 1 boat and go up the river, and Trevor takes the other boat and goes down the river. The 2 boats have identical top speeds in still water. After 3 hours of traveling at the boat's top speed, Michael and Franklin are 8 miles up the river, and Trevor is 24 miles down the river. Determine the speed of each boat in still water and the speed of the river's current. Okay. So we have some interesting stuff that we have going on here. So we have some distances that are showing up. We have a time, and we have at least 2 speeds showing up. We have the speed of the boats, or speed of each boat in still water, and the speed of the river's current, which implies that this thing is river's moving in some direction, some way, shape, or form at some speed. So this is where I'm going to scroll up here. We're trying to figure out, okay, what general equations might we be using if we have a distance, a rate, and a time. We're probably going to end up using this distance formula, a DIRT formula, if you want to call it that as well. So we're going to be using our distance formula to help us out with this. Number 2 here is the one that we are going to reference, and I'm going to jump us over to our Blackboard and go through how do we set this thing up. So jumping on over there. There we go. So looking at example 2, now if we need to, we have a lot of just generality of some stuff that's going on. I think it's sometimes helpful, again, to write some or draw some sort of a picture that represents this. So my recommendation, so we get the visual and we can keep an idea of what's going on here. Because compared to our previous distance, rate, and time problems, we've got an extra, should we say, dimension of things that are going on. We've got a distance, 2 rates, the rate of each boat and the rate of the current, the river's current that's going on there, and a time. So I think it could be helpful to draw a quick picture of this thing. So that's what I'm going to do. So we're assuming they're starting at the same point as what's given to us. I'm just going to make, here's our quick river. If you've got pens or something like that, some color. There you go. There's the river, there's the current. Now I'm going to choose, just for the sake of having a visual of this, let's write this out for ourselves. The current's direction. We're going to have it move from left to right. So the current is going left to right in our picture. Okay. Now reading back through the problem, we'll go to the specific parts that we need. Michael and Franklin take 1 boat and go up the river, and Trevor takes the other boat and goes down the river. So we have the instances of, make sure we got our colors here. So we have the instance from the starting point that we have here. We have one of them that is going up the river. Make this a bit straighter of a line here. Going upriver. So this is Michael and Franklin going up the river. And then we have Trevor, who is going down the river, meaning he's going with the current. Okay. So now we at least have some sort of a quick silly visual of what this thing looks like to reference for ourselves. And again, I think making these visuals is very helpful, especially with story problems like this, where we can actually get some sort of a visual of what's going on in our head. But again, we're going to let the paper or Blackboard, in this instance, hold on to that visual for us while we start filling in some information. Now, we were told, again, we're working with our distance, rate, and time problems. So I recommend that we go through and let's set up a table for ourselves. At least maybe we can fill in some information on our picture. Maybe we can fill some stuff in on a table. So like we've done previously. So we have our distance in miles. We have a rate. It's a bit straighter here. And what unit are we working with this? Well, it doesn't explicitly say, but our time is in hours. So it stands to reason that our rate is going to be in miles per hour. And then we have our two scenarios that we're working with. We have the instance where we have Michael and Franklin, and the instance where we were working with Trevor. So now we have our parts of our table set up for ourselves, and now we're going to start filling things in accordingly. So let's go with, I'll reread our problem again so we can get an idea of this visual and the other stuff that we've been given. So Michael, Franklin, and Trevor are attempting to get away from a local motorcycle club. They decided to lose the motorcycle club members by taking two boats from the same dock and splitting up along a river. So again, with our visual that we have right above there, that's essentially telling us they're starting from the same point. One boat's going upriver, one boat's going downriver. So we have that visual represented for ourselves. The two boats have identical top speeds in still water. After 3 hours of traveling at the boat's top speed, Michael and Franklin are 8 miles up the river, and Trevor is 24 miles down the river. Determine the speed of each boat in still water and the speed of the river's current. So we need to start filling in things inside this table from that. So do I know the distance that Michael and Franklin traveled? And we do. It's telling us that Michael and Franklin are 8 miles up the river. Another way of saying they traveled 8 miles from the starting point. Let's make that a better 8 here. There we go. And we're told that Trevor is 24 miles down the river. So his distance would be 24. We also know the time that they both traveled. We're told after 3 hours of traveling at the boat's top speed, so each group traveled for 3 hours. We know how far they went. Now, here's the tricky part with this. We have been told the two boats have identical top speeds in still water. But based on what we are being asked to solve for, the last sentence says, determine the speed of each boat in still water and the speed of the river's current. So that means that the river does have a speed that is associated with it. We have to determine what that's going to be as well. And what's going to happen in the context of this problem is that current speed is actually going to affect the speed of each of these two scenarios. If we look at the one on the left, staring on the left over here, the instance where Michael and Franklin are going up the river, it stands to reason that if they are going up the river, they are going against the current speed. So whatever their top speed is, it's going to be reduced by the speed of the river's current. So I'm going to let R represent the rate of the boat, and their overall speed is being reduced by the speed of the current because they're going against it. Going off of this as well, if we're looking at the instance for Trevor, we're told Trevor is going, exact wording on here with this, let me find it. Trevor takes the other boat and goes down the river. instance that we have here on the right. So based on how we have defined the current's direction, that's how it influenced our drawing. So in this regard, Trevor's speed is the boat's top speed plus, well, should probably switch over to a pen. So it's the boat's top speed plus the speed of the current, because it's going with the river's top speed, the river's current that's going on. It's helping him go faster in that regard. Now you can see different problems that work with a similar idea. Wind resistance is a big one. If you think of it from the standpoint of, if you have a plane that's flying, is it going with the speed or with the wind speed? Is it going into the wind speed? Something to that effect. So with this instance, we now have our distance, rate, and time for each of these scenarios. Okay. So now we have a couple options in how we do or don't want to go about solving for this thing. But I would recommend the first thing that we're going to do, let's rewrite each of these things into our general equations here. So again, taking our general equation for distance is equal to rate times time, or dirt. So let's translate this thing over here, each of these ones over. So the distance that Michael and Franklin traveled, 8 miles. Their rate was the rate of the boat minus the current of the river, because they're working against it. And the time that they spent doing that traveling was 3 hours. So we're following the same process for Trevor's. His was, he traveled 24 miles. His speed was the boat's top speed plus the speed of the river. And he also traveled for 3 hours. Okay. So fantastic. We have 2 unknowns and we have 2 equations written out for ourselves, which is fantastic. Now here's the part where there's some variability in how we can go about solving this thing. So there's a lot of thought that we've done previously where we said, okay, well, I want to solve this thing for, maybe I want to solve it for one variable and then go from there and see what happens. If nothing else, let's take a look at this thing as a system of equations. We have our substitution method and we have our elimination method that we can use to help us out and solve this thing. I'm going to move us down here, just rewrite these right below. So we have our system of equations. Okay, so fantastic. Now we need to determine, do we want to use our substitution method or our elimination method to go through and solve this thing? We don't need to choose that for ourselves right now. Let's simplify the right side of both of these equations, because we have r minus c times 3 and r plus c times 3 on the right-hand side for both. So let's simplify those things, see what comes out of it. Maybe that will help us determine if we use the substitution or the elimination method. So if this 3 distributes through to everything on the right-hand side of the equation, whoops, to everything, there we go. So we get this. We'd rewrite and simplify the right side of both of these equations that we started with. And we're finding, at least I'm noticing this, of our c variables, the coefficients, the numbers in front of them, are additive inverses of one another. Meaning that if we wanted to use the elimination method, these things would cancel each other out, which would be fantastic. Okay. We also have the option, if we wanted to, we could say, all right, well, fantastic, but I want to use the elimination method to solve this or anything like that. We have a lot of options at our disposal. It's our choice on which one we want to use, and then we need to move forward with it. So in this instance, I'm going to say that we use the elimination method because that's going to cancel one of these things out right here. When you are going through and solving these, it's your choice, whichever method you would like to use. We're going to use the elimination method here. So because we have additive inverses, we are going to be adding these things together vertically. So 8 plus 24, that's going to give me 32. 3r plus 3r, that's going to give me 6r. And then negative 3c plus 3c, those are going to cancel. It's going to be gone entirely. So now I have 32 is equal to 6r. I don't want 6r, I just want 1r. So I'm dividing both sides by 6. 32 divided by 6. I don't know what that number is off the top of my head, so I'm just going to apply a calculator off screen. And we have not been told anywhere in here that we want to have a mixed number or fraction or decimal or anything like that. So let's see, what does this thing look like as a fraction? It's going to be 16 over 3. We can also rewrite this. We'll put it out in both forms. Oops. There we go. So this thing would be 5.3 repeating forever. Okay. So we have the rate of the boats, and now we determine the rate of the river's current. So the way we go about doing that, now we're using the elimination method. So I'm choosing either of my original formulas, my original equations that I started with. And why not? We'll go with equation 2. So I'm going to write out the original, don't put the 0 in there. There we go. Write out the original equation and substitute in what we're working with. So I'm going to substitute this thing in as a fraction because I like fractions over decimals a heck of a lot more. So we substituted that in for our rate, the rate of the boat, the top speed of the boat. This 3 is going to distribute through to both terms. So when that happens, we're going to get 16 plus 3c. The 3 going through the fraction, the 16 is going to stay the same. The 3's cancel out. Subtract 16 from both sides. It's going to give me, what's going to be 8. It's equal to 3c. Divide both sides by 3. And we're getting c is equal to 8 over 3. Or as a decimal, go 8 divided by 3. I think that's going to be 2.66 repeating. And those will be rounding accordingly. On the test, I would specify round your final answer to the nearest 1, 2, how many decimal places from there. But this, again, example of how we could set up a story problem and how now we have the elimination method at our disposal to help us go through and solve these things. So a fair amount of this setup, move this around here a little bit. A fair amount of this setup should be familiar to us in that we have done and worked with this before, especially with our distance, rate, and time problems. So how we set these things up, how to write these things out for ourselves, anything like that. Okay. And again, if you need to make a silly little picture for yourself, you guys see how much of an artist I am. So Something like this, if that helps you out with keeping a visual of what's going on, use it. Nothing wrong with that. But now, as we're going through and after we have everything set up for ourselves, we have this system of equations, we now have the option, if the problem does not specify, to use a certain method over another. We can use either the substitution method or the elimination method to go through and solve this thing. And again, on the test, I will be specifying if I am looking for you guys to solve this thing using the substitution method, I will state that in the problem. If I'm looking for you to use the elimination method, I will state that in the problem. If the problem does not state use either of those two methods, then that means either one is on the table. You can use whichever one you would like. I don't care at that point in time, at least for that problem. Okay? So make sure you are reading through the directions, because that will tell you whether you're going to use one method or the other, or if it's your choice on which one you would like to use. Okay? I know some people, as they go through and work on problems like these, they tend to prefer one method over the other. Again, it's on a personal preference level on which one you would like, or you do like more than others, but you can only use that one. Again, if I'm specifying use that method, or you have the option to use that. So make sure you're reading the directions, and the question itself, make sure you are doing what it asks you to do, including the method that's asking you to use. Okay. So let's take a look at our third example in this section. Move this over here. Okay. So Jeff and Ryan are building a new stone castle in Minecraft together. Shout out to anyone who's out there and plays Minecraft or has kids or anything like that to play Minecraft. It's taken the world by storm all these years. Because this thing is going to be massive, they determined they need to take 2 days to assemble all of the blocks of stone they need. On the first day, they put in 4 hours of work each and collected a combined 2,500 blocks of stone. On the second day, Jeff worked for 3 hours and Ryan worked for 5, for a combined total of 2,805 blocks gathered together. Determine how many bricks per hour Jeff and Ryan were individually able to gather. Okay. So this is an instance where we're going to be using one of our our new equations that we have. It's that super generalized one that we worked with, or that I mentioned at the start of our lecture yesterday. So I'm going to go over to that one. This is where we are going to be using our, what's up here, our rate principle. An amount is equal to a rate times a base. So the amount of something is equal to a rate and a base that we have here. So to think of, okay, what kind of a rate are we working with? What's an amount? A base could be a time. It could be, there's any number of things actually the base could be, but it's a very generalized equation that we are working with. The distance formula, the distance equals to rate times time, this is actually a really great example of a type of rate problem, the rate principle that we are working with. So it's an amount of something equaling to a rate times a base. So this is the equation that we're going to use. I'm going to work with it very similarly to the distance, rate, time problem, except, again, just the generalized version of it. So we go back to our problem. We have here. So trying to pick out some information that we have. We have in a total amount of blocks they have for the first day, because we're told they're working over 2 days. So the first instance of the first day, they put in 4 hours of work each and collected a combined total of 2,500 blocks of stone. Okay. Then we're told on the second day, Jeff worked for only 3 hours and Ryan worked for 5 for a combined total of 2,805 blocks of stone gathered. Determine how many bricks per hour Jeff and Ryan are individually able to gather. So we actually don't know what the rate that Jeff can gather at and the rate that Ryan can gather at. They could be the same, they could be different, but we do not know at this point in time. So we need to work with the idea of how can we build an equation or some equations that are going to work with both of these instances. So I'm going to jump us over to our Blackboard, and we'll start going through our instances that we have here, or how we set this thing up. So first and foremost, we are looking for how many bricks per hour Jeff and Ryan are individually able to gather. So I'm going to go ahead and make those two unknowns into some variables for myself. So I'm going to use G to be, call it Jeff's gather rate. Okay. And then I'm going to use R to be Ryan's gather rate. Okay. And again, our general formula was amount is equal to a rate times time. And there is some variability to this as we go through and solve these things, but that's the general idea that we have behind it. So as we're looking at this, rereading our problem, we have 2 days of information that we are working with. So we're going to look at day 1 first and foremost. Again, we're going to solve these things in parts. I find that people that try and do everything all at once, we generally get lost on what we're doing, and then bad things happen from there. So let's just look at day 1. So reading this out from the problem again. On the first day, they put in 4 hours of work each and collected a combined 2,500 blocks of stone. So we have some buzzwords that are showing up in there, kind of our English to algebra. Combined, so it tells us basically a total. We said, okay, so Jeff gathers blocks at a certain rate, Ryan gathers blocks at a certain rate. They worked for 4 hours, and their combined total was 2,500 blocks of stone. So a couple ways we could write that out for ourselves. The total that they had was 2,500. Okay. Now, if we think on Jeff's work individually. He gathers blocks at some rate. We don't know what that rate is, but he gathers blocks at some rate. We also know that he put in 4 hours of work to do that. So how many total blocks what was the amount of blocks that Jeff gathered? Well, the amount that Jeff did is going to be his gather rate, which is G, times the total number of hours that he spent working on this thing, which is 4. So based on our definition of an amount is equal to a rate times time, the amount of blocks that Jeff gathered is equal to his gather rate times the number of hours that he worked. So that gives us Jeff's amount. Now we know Ryan also worked with him that same day. We do not know Ryan's speed, which again is, or gather speed, which is fine. But we know that their combined total was that 2,500. So I have the amount that Jeff gathered, and I'm adding the amount that Ryan gathered. So again, I don't know Ryan's gathering speed or gather rate, so I'm going to leave that be R as the variable we defined right up above here, right up here. So it's going to be Ryan's gather rate times the number of hours that Ryan worked, which we also know to be 4 hours. So we have an equation set aside for day 1. Let's reread that sentence and see if it makes sense for ourselves. On the first day, they put in 4 hours of work each and collected a combined 2,500 blocks of stone. So the amount that Jeff gathered plus the amount that Ryan gathered equals the total of 2,500 blocks. So we're good there. Now let's take a look at day 2. So dividing this thing up, we're just solving it in parts as we're making our equations. We have 2 unknowns, so we need 2 equations. We're just, again, looking at it in pieces. So on the second day, Jeff worked for only 3 hours, and Ryan worked for 5, for a combined total of 2,805 blocks of stone gathered. Okay. So a combined total of 2,805 blocks of stone gathered. So we have a total there. So it's that 2,805. Now, very similar to what we did in the first day's worth of work that we have here, we do not know Jeff's gather rate, but we do know the time that he worked doing that. So we know how many blocks did Jeff gather on the second day? Well, it's going to be the rate that he gathers at, which is that G value, times the number of hours that he worked, which was 3. Trying to determine, okay, well, what was the amount that Ryan gathered on the second day? And again, we don't know his gather rate, but that's fine. We can solve for that. So he had some rate that he gathered at, and he worked for 5 hours. So we know his time. So once again, very similar to day 1, Jeff's amount that he gathered is equal to his rate times his time. The amount that Ryan gathered is equal to his rate times the time that he spent gathering. So now we have an equation for day 1. We have an equation for day 2. Let's bring these together and rewrite them as a system of equations. And I'm looking for space. Let's put it right down below here. Oh no, computer's starting to lag a little bit on me. There we go. So now we have our system of equations. We have our first equation, we have our second equation. And now, with this system of equations, we have not been told that we need to use one method or the other. So at this point, it's now your choice. If you're going through this on the homework or on the test, it is now your choice on whether you would like to solve this thing using the substitution method, or if you would like to solve this thing using the elimination method. Either option works. We just need to pick one and move forward with it, which I'm hoping is becoming abundantly clear when we go through a lot of these problems that that's what we're going to do. So I am not seeing generally the thing for me personally, I like to look at each of these variables and see, okay, are there additive inverses already to go for me at the very beginning? There aren't any for the G variable, and there aren't any for the R variable. At this point, if that was the case, we did have that, kind of like our previous problem, that's generally when me personally, I like to go with using the elimination method. If that's not the case, yeah, then it's a little bit more of a toss-up with how we want to do this. So I'm going to use, just for the sake of using something different from our previous one, I am going to use the substitution method to solve this thing. So our substitution method says we need to solve one of the equations for one of the variables. Doesn't matter which one, say it with me. You just need to pick one and move forward with it, right? So I'm going to choose to solve for equation 1, and I'm going to choose to solve equation 1 for R, because I feel like it. So we'll use the substitution method. So you can follow what we're using here. Okay, so solving my first equation for R. So writing that out for myself. So I'm treating everything else as though, or all other variables, as if they were just numbers with how I can add, subtract, multiply, and divide them to both sides. And then from here, I'm dividing both sides of this equation, meaning every single term, by 4, because I don't want 4r, I just want 1r. And then what's that? Applying the calculator, because I don't know what that number is off the top of my head, so I'm just using that off screen. 625. So now that I have solved one of the equations for one of the variables, now I can plug that in for that variable in the other equation. Give us a little bit of a separator here. So I solved the first equation for r, which means I need to plug in the thing that I just found for r into the second equation that we have for ourselves. So our second equation, I'm going to check this at the top here just to make sure I have that written out correctly. I believe that's it. Yep, that's the one. So wherever an r shows up in my second equation, plugging that in there. So now, using the distributive property, I'm going through and I'm solving for g. And again, we're going to have larger numbers showing up with this. Again, that's fine. Apply your calculator. Combine like terms on the right-hand side. This up here just a little bit. I'm running out of space. And then I'm solving for g, so I need to get rid of everything else, all the other terms on that right-hand side. Then apply the calculator on the left-hand side, because I don't know what that number is going to end up being. So let's see, so 2805 minus 3125. So I've got that there. It's negative 320. Divide both sides by negative 2. And again, apply a calculator if you need to. Nothing wrong with that. I'm getting 160 on the left-hand side. So I get g is equal to 160. And g represents the rate that Jeff is gathering those blocks of stone. Now I do also need to find Ryan's rate, but I already have this one, so now, again, following our substitution method, I have found one of my variables. I can plug that in for that corresponding variable in either of my two original equations and find what's left over. So we have our g value of 160. So let's back up here. Separate us out just over here a little bit. So again, we can choose either of our two original equations to work with and find our r value. I'm going to choose the first equation because I feel like it. If you want to use the second equation, you could use that also, but either one works. What am I going to say? You just have to pick one and move forward with it, right? I think that should maybe be on a t-shirt or something. Maybe not, I don't know. So we found our g value, so I'm just plugging that in. So now that I have that plugged in there, I'm simplifying both sides, and now I'm solving for r. So mechanical problem, like we've done back in the chapter 2 material, I think. But it should be a review at this point. Subtracting 640 from both sides. Again, calculating and crunching those numbers off screen, but you're welcome to use a calculator to do that and do that number crunching for yourself, because these numbers are going to get big, they're going to get gross. There's a reason you guys have a calculator, to deal with stuff like that and stuff like this. So I'm getting 465 is equal to r. So what's the rate that Ryan gathers those stone blocks? Well, he gathers them at 465 stone blocks per hour, compared to Jeff's 160. Zoom this out here a little bit. So we have our two answers there. So again, this was going through and solving it using the substitution method. If you are working on this at home or anything like that, and again, the problem does not specify solve this using the substitution method or the elimination method, then it is 100% your call as to which method you would like to use to go through and solve this thing. But again, the big part with a lot of these is going through and setting up our equation, or two equations that we might need accordingly. Again, this amount equation, this amount equaling a rate times a time, this is an extraordinarily generalized equation compared to our dirt one. So we might need to be using this in slightly unconventional ways, in the sense of this is an amount, plus this is an amount, with a slightly different way of writing it, plus this amount, which is another slightly different way of writing it as before. So again, we can think of it as the total amount is equal to Jeff's amount plus Ryan's amount. The total amount is equal to Jeff's amount plus Ryan's amount. Again, depending on which day we are looking at. So different ways of writing these things out, different ways of equating them based on the information and the equations that we are going to be using for that problem. So don't rush yourself if you are going through and working on these setup portions of these problems, because again, this is absolutely vital. Read, reread, reread again, and reread again and again and again and again as you need to with these problems. You cannot emphasize that enough. A lot of people just try and quickly read it once and bam, there's equations, and I'm just going to solve these equations and I'm just making up. Don't be that person. Take the extra time that you need, if you need it, to go through and methodically write everything out for yourself. There is nothing wrong with that. I'll put money on you'll find that you'll get the correct answer more often than not if you're doing that, versus just flying through it. Okay, so we'll divide this part up here on our Blackboard, and we'll take a look at example 4 over in the lecture notes. Okay, so jumping back over to our lecture notes. Okay. So the first semester, Morty is enrolled at Green River College. He earned the following grades: a C in a 3-credit English class, A in a 4-credit science class, B in a 3-credit speech class, and C in a 4-credit psychology class. Rick thinks Morty should just drop out of college and join him on interdimensional adventures instead. I mean, he pretty much spells that out in one of the episodes, so that makes sense. So we're assuming that an A is a 4.0, B is a 3.0, 2 is a C is a 2.0, and D is a 1.0, F is a 0.0. So think of it as grade points in this regard. So we have two parts to this. First, we are told determine Morty's GPA for his first semester. So we're saying, okay, we know he earned grades in each of these classes, but what is his total GPA going to be for that semester? So I'll go back up to the start of our 5.4 and 5.5 notes. We'll take a look at the equation that we're going to use for this. So our one that we're going to use for GPA is the sum of the grade points that we have divided by the sum of the credit hours that we have. And it's important to note that when we are going through this, and this is also something you can apply to your own overall grades, your own GPA here at Green River, it's not just the grade that you earn in the class that's going to influence the GPA, it is also how many credits the class is worth. The main point being, a 1 credit class versus a 5 credit class are going to be weighted differently on your total GPA. The 5 credit class is going to have a significant larger weight to it. You can think of it as the weights of classes. This is all something that instructors do, myself included, of weighting grades. So a portion of your grade has this weight, maybe homework has this weight, tests have another weight, a project has another weight in the overall total of your class. So GPA is calculated very similarly. So we need to include not just the grade points that you earned, or that Morty earned, but also the credits that went along with, or how many credits each class was worth to make that happen. So we are going to go through that, but we are going to be referencing our GPA formula for this problem. So I'll go back down to it. And as we're seeing here, we're being told a grade of C in a 3 credit, A in a 4 credit, B in a 3 credit, and C in a 4 credit. So A, B, C, D, and F each has grade points associated with it, as would be listed for you. If this showed up on the test as well, I would give you guys something similar to this of what he earned for grade points. Or I would tell you maybe instead of a C, he earned a 2.2 or something like that. I would give you guys the GPA or some way to calculate that on the test. It's absolutely impossible to solve this thing without having some sort of grade to GPA converter or the GPA not given to you guys. So we need to take into account the grade points that were earned and the credit load that each class has, the credit weight, I should say, that each class has associated with it. So for our first part, we're going to go through part A, but we're going to determine Morty's GPA in his first semester. So we'll jump on over to our Blackboard and we'll get started on that over there. So let's we'll work with 4A in here. So I'll relist each of these things, the grade that we have over on the Blackboard that we have here. So we have an English class. I also recommend that if you're going through this on the homework of the test, that you do this for yourself as well. So for the English class, it's 3 credits. He had a C, which is equal to how many grade points? Based on the converter that's given to us, that's equal to a 2.0. So we're going to list each of the classes and each of the information that we have for each of those. So it's English class, we have a science class, which was 4 credits. And he earned an A, which was a 4.0. He had a speech class, which was 3 credits. And he earned a B, which is equivalent to a 3.0. And then lastly, he had a psych class, or psychology class. And that was a 4 credit class. And he earned a C, which is also equivalent to a 2.0. So we have each of the classes, we have each of the credits, and we have each of the GPAs associated with them. So all we do is translate from the problem given to us into our paper or our Blackboard as we're working through it. So now we need to list off for ourselves, okay, we're trying to find his GPA. So how do we, need a way better G than that. There we go. What is his GPA? Well, based on how we had presented to ourselves, it's the sum of the grade points divided by the total credits that he earned. So we do need to take into account, okay, the credits and the grade. So we're going to go through each of these classes piece by piece, and then we'll figure out how to write each of these down. So the English class, he has 3 credits at a 2.0. So we're going to list that in the numerator of this as 3 credits at a 2.0. So we are including the weight along with the grade because we do need to take that into account with each of these. And we're doing this for each of the classes. So we had a 3 credits at 2.0 plus 4 credits at a 4.0, the science class. Extend this out here a little bit because we're going to need some more space. Then he had 3 credits at a 3.0, and then 4 credits at a 2.0. Oops, put this over here. So I am not only adding the number of grade points that he earned, but I'm also adding in the weight that each class has associated with that GPA. Again, going back to our general idea of the number of credits, the weight of a class is something that we absolutely need to take into account when we're calculating total GPA. A larger credit class is going to have a larger impact on an overall GPA than a smaller credit class. And this is how we take that into account. So the numerator would be the number of credits times the GPA earned for each of the classes that we're taking a look at. Now the denominator, based on how we have that written out, it is the sum of the credits that he earned. So in our denominator, we're just going to add the credits together. So he had a 3 credit class, was the English class, plus a 4 credit class, which was the science class, plus a 3 credit class, which was speech, and then plus a 4 credit class, which was the psychology class. So the GPA problems differ from our previous ones that we've just worked on from the sense of we're just going to be doing some number crunching after we have gotten all of this set up for ourselves. But this is the key essential part with all of these, making sure we have the credit and the GPA, credit GPA, credit GPA, credit GPA listed correctly. And then make sure, again, we're just adding the total number of credits together down below for our denominator. And at this point in time, now we're just going to apply the calculator and let it number crunch everything in the numerator for us. You can let it number crunch everything in the denominator for you as well. That's what I'm going to be doing off screen. So you can quite literally type in 3 times 2 plus 4 times 4 plus 3 times 3 plus 4 times 2. And that's going to give you your numerator, 3 plus 4 plus 3 plus 4 for the denominator. So I'm going to do that off screen, but that's where I'm going to be getting the resulting numbers. You're welcome to do that also. Take a quick second here. Oops, 3 times 2 times 4. Okay, and I am getting 39 for the numerator, and then it's going to be 7 and 7, so it's going to be 14 for the denominator. Now we're not done. We need to know what the actual GPA is going to be, so 39 divided by 14. And most GPAs, or at least we have not been told in this one where we are going to round this thing to. So if you do 39 divided by 14, that can go on forever. We are going to round this thing to 2 decimal places. Again, the problem hasn't stated it for us. On the test, I would specify that for you guys. And actually, you know, we're going to do it to 1 decimal place because the A, B, and C is listed out that way. So rounding our final answer of 39 divided by 14, rounding it to 1 decimal place, that's going to be equivalent to 2.8. So what is Morty's GPA for his first semester at Green River? He earned a 2.8 in total. So that is part 1, or part A, I should say, for us. So let's jump back to our problem, because we do have a part B. We'll go through how do we solve this thing. So part B is asking, Morty wants to raise his GPA to a 3.0. How many credits with a grade of an A must Morty take to meet this goal? So we already have a first semester's worth of classes under our belt. We're assuming he's going to get a grade of an A on all of his classes moving forward, but we don't know how many credits he needs at an A to move forward with that. We also know what his desired GPA is. He wants it to be a 3.0. So we're going to have to take our original general equation for the GPA and we're going to modify it a little bit based on this particular problem that we're being asked about. But this is the problem we're taking a look at. We'll jump on over and go through it. So looking at part B, again, we have our general equation of a GPA is equal to the sum of the grade points divided by the sum of the credits. Now in this instance, we have been given the resulting GPA that we want. We want the result to be a 3.0. So first things first, we're going to write in 3.0. We know what he wants his GPA to be. And now we need to fill in the fraction accordingly. So just like we did previously, we're going to be determining, okay, well, how many classes is he going to take, and with how much of a GPA is he, or what GPA is he earning in each of those classes? Now we have a couple options here. You could go through and list each of the classes that he took previously, just like we did up here. The 3 credits out of 2, 4 credits out of 4, 3 credits out of 3, and so on. You could list all of those. You could then list down below the credits that he earned as 3 plus 4, or plus 3 plus 4, and so on. Or we can save ourselves some time and determine, well, I already know what all of this information culminates to. We know he has a GPA of 2.8 with 14 credit hours. So I can plug that in at the very top of my fraction right up here. Because again, the sum of the grade points that we have in total. So we already know 14 credits he has a 2.8 in. And that's what he earned in his first semester. Now the problem is asking us, how many credits with a grade of an A must Morty take to meet his goal? So he already has 14 credits at a 2.8. We are assuming he is going to be earning an A, which is a 4.0, on all of his future credits that he's going to take. But we do not know how many credits that's going to be. So how do we write that in? Well, just like we did with our previous ones, we have our credit number times the GPA. The difference here is we do not know how many credits he's going to be taking. So in the numerator, this is going to look like, oops, it's better plus in here. How many credit hours has he taken? Unknown. What's the GPA associated with those, though? That's going to be a 4.0. So he already has 14 credits at a 2.8. And he's going to be taking an additional X many credits at a 4.0. We're assuming he's getting a 4.0 based on what the problem has told us. We do not know how many credits that's going to be, which is fine, but that's why we are listing it as X in there for the number of credits he's taking. Now, for our denominator, we are adding up the total number of credits that he's going to be having, or what he's going to be taking for this for future semesters. And that's going to be that 14 credits plus the unknown number of credits, that x, that's going to be at a 4.0. We don't know that amount, we don't know that value, but we have to list that they're all the same, which is fine if we leave it as an unknown. Okay. So this is how we set up our problems where we are trying to find how many credits at a certain GPA to earn an overall GPA of something else like that. So this is our setup for that. Now from here, to actually go through and solve this thing, we have a couple options of what we can do here. We can simplify the numerator on the right-hand side, and then we can worry about canceling fractions from there. Or we can start with canceling the fraction from the very beginning. So we have a couple options here. We can determine what is the lowest common denominator between all fractions in this problem, which we only have one explicitly written fraction here. So our lowest common denominator would be 14 plus x. So I can multiply both sides of my equation by 14 plus x. That will eliminate the fraction on the right-hand side, and that will give us some sort of algebraic expression on the left-hand side. Perfectly viable option that you can use. Your other option, if you wanted to, 3.0 is basically the same as saying 3 over 1. And now in this instance, I essentially have a fraction equals a fraction. When we were working with proportions earlier in the quarter, we have the option of when a fraction equals a fraction to cross multiply. So the numerator times the denominator, and then the denominator here times the numerator up here. So you can either multiply both sides by 14 plus x, or you can cross multiply and get rid of the fraction that way. Either option works. What am I going to say next? You just have to pick one and move forward with it, right? So for this, I am going to choose to multiply both sides by 14 plus x. I think it's a bit more straightforward. It's a bit less to keep track of in doing so, but again, it's your choice on which one you would like to use. So I'm going to multiply the left and the right side by 14 plus x. I'm a little low on space over here, so bear with that on the left-hand side. Actually write plus, not weird t. There we go. So when we do this, fraction cancels on the right-hand side and the left. Hold on. The left-hand side, we have 14 plus x times 3 is equal to this here, the numerator over here. Now again, my recommendation for you when you are doing this, you are just eliminating the fraction in the first line of work. Nothing wrong with that. I would be very, very, very cautious on how much you're going to cancel and multiply together in your next line of work. The exact reason of a lot of people will do stuff that they shouldn't be doing, or they will forget to do things in that regard. So if you need to just write it out for yourself, kind of like I have written out here, do it. Nothing wrong with taking an extra line or two of work to make sure you're doing your work correctly, not just quickly. So I'm simplifying each side of the equation down. I have 3 times 14 on the left-hand side. That's going to give me 42 plus 3x. On the right-hand side, I get 14 times 2.8. That's going to be 39.2 plus 4x. And this is better 4. And this is better 4. There we go. Now I have variables on both sides of my equation. I don't want that. Getting rid of the smallest variables because I don't want a division by negatives if I can help it. Let's get that there. And then I don't want 39.2 plus x. I just want that x all by itself. And then 42 minus 39.2. So I have 2.8 equals x. So x represents our number of credits that we need to take. So let's take a quick moment to think on this, because this is the last thing that we need to do in our story problems. Is this a reasonable answer? Has anyone ever heard of a 2.8 credit class? And I haven't. I've heard of a 2 credit class, I've heard of a 3 credit class, I've heard of a 1 credit class. I have never heard of a fraction of a credit class ever before. So in the context of this problem, if he needs 2.8 credits, what's the only reasonable answer that we could have? Well, he can't have 2 credits because that's going to be below the 2.8 that exact 2.8 that he needs. But the only realistic number of credits that he can take that's going to meet that or exceed it is if he has 3 credits. So when we're asked how many credits with a grade of an A must Morty take to earn his goal, he cannot take 2.8 credits, but if he takes 3 credits, he will at least meet his goal, and he might exceed it by a little bit, but that will at least have him meeting his goal. So Morty needs 3 credits. And that is going to be our final answer. So this is the instance where the raw mathematical answer is one thing. The actual real world answer that we can use for this is going to be something slightly different. So yes, 3 credits is higher than the 2.8, but we know if he gets this at the very least, he will earn that 3.0. So 3 credits, he's definitely going to get it from there. Okay. So this is our process for going through our GPA problems. So make sure you are keeping track of, am I actually solving for a GPA like we had in our first part? And again, make sure you're listing the number of credits and the GPA associated with those credits in the numerator spot. Make sure you're doing just the credits in the denominator spot as well. That's going to give you the GPA. If you're solving for the number of credits that you would need for something, make sure you are modifying your equation accordingly. Do I know my GPA? Do I know some of the credits? Do I know all of the credits? Do I know anything like that? So these GPA problems, they do tend to differ from the previous ones we've done where we're working with a system of equations. In this instance, we're just plugging some things in to an equation and just solving them individually. But same idea holds true of maybe you want to rewrite all of this out for yourself. I think doing this is really, really helpful again, from an organizational standpoint. So if you need to do this for yourself, do it. Again, we want to be doing these problems correctly, not just quickly. So do what you need to organize it for yourself as you're going through and solving these on your own. Maybe you organize a little bit differently than what I did. Your call. Do what works for you. All right, so I'm going to end our recording there for today, and then we'll move on from there accordingly.